Stage 1 is to draw a diagram showing all the forces and any acceleration if it exists. The mass is 3, so the weight is 3g. There's obviously going to be a normal reaction R. There's a horizontal force of 25 which causes it to be on the point of moving up the plane, so it must be that way. It couldn't be the opposite way. And because it's on the point of moving up the plane, friction always opposes motion, so it's going to be down. Make sure your arrows are very long. There's no acceleration in the question, so this is finished. There's no acceleration, so it's an equilibrium or statics question, so we're going to resolve parallel to the slope to find F, perpendicular to the slope to find R, and we've got a quote from the question. The question says, on the point of slipping, that will justify F equals mu R. The two forces which are not already parallel or perpendicular to the plane needs to be resolved into the components which are. Here's the original angle of 30 degrees. If we chase it round, we get 30 degrees here and here. And in each case, starting with the 3g, we need to make the original force the hypotenuse of the right angle triangle, opposite the right angle. So this is now resolved into a component here, 3g cos 30 degrees, because it's adjacent to the angle. And this component here, which would be 3g sine 30 degrees, same magnitude and same direction, but I'm going to draw it up here, 3g sine 30 degrees, because we want our forces to be connected to the body here, or going through the same point. We do the same thing with the force of 25, but before we do, this original 3g force needs to be put in brackets. It's not there anymore. It's been replaced by its two components. We can do the same thing with the force of 25. So again, it's the hypotenuse of a right angle triangle. The component adjacent to the angle is 25 cos 30 degrees. The component which is opposite the angle, which is 25 sine 30 degrees, is going to be drawn here, connected to the body, same magnitude, same direction. 25 sine 30 degrees, and then the original force is put in brackets. It's not really there, it's been replaced by its components. Now look ahead to the equations. Perpendicular to the plane, we've got R out of the plane is equal to 25 sine 30 plus 3g cos 30 away from the plane, or into the plane rather, and parallel to the plane we've got F plus 3g sine 30 equals 25 cos 30. So we'll put those into equations. Here are those three equations as we planned. What we can see is from the first one, equation 1, we'll be able to subtract 3g sine 30 from both sides, and just using our calculator we'll work out F. The second equation, again just using our calculator, we'll work out R, and then once we know F and R we can substitute them into the third equation and we'll be able to find mu. So in exactly that way, from equation 1 we've worked out F, and we put that in memory A in the calculator for later. From equation 2 work out R and put that in memory B. From equation 3, mu equals F over R, which is that number, and now for the final answer we think UAU. Units, there aren't any, because the coefficient of friction is a force divided by a force. Accuracy, we use G equals 9.8, so the degree of accuracy is going to be two significant figures, and then underline. That's the end of the question, but I just want to talk a little bit about equation strategy. Normally in these cases you either resolve parallel and perpendicular to the slope, which is what we've done, or you resolve horizontally and vertically. You're going to get the right answer in either case as long as you're careful, but why has it been more efficient in this case to do parallel and perpendicular? On the surface it makes no difference. If you resolve parallel and perpendicular like we did, then you've got to split two forces up into components. If you'd chosen to do horizontal and vertical, you've still got two forces to split up into components, R and F. But if you had done it like that, then the force R being split up into components would appear in both equations, and the force F being split up into components would have appeared in both equations. We'd have had simultaneous equations to solve in the pure maths phase, and it would be okay, but just a little bit more hassle. So in this case, because we knew we wanted to find out R, and we knew we wanted to find out F, in order to substitute into F equals mu R, it was better to do parallel and perpendicular.